Okay, so I've taken this side right here and I've written it in terms of sines and cosines, and complex fractions come up all the time, so you've got to know how to deal with these. So what we're going to do is, because we never divide by a fraction, we're going to take the bottom and we're going to flip it over and we're going to multiply. So that's going to put a sine on the top, it's going to put a cosine on the bottom, and then what's going to happen? Okay, this is called cross cancellation. You should be really good at this. I'd cancel this one off with one of those, and here's what I've got. I've got 1 over sine of theta times 1 over cosine of theta. So from here to here, I used, this was a reciprocal identity, this was a quotient identity, and this was a property of, or I'd just say complex fractions. And then take a look at what we've got and take a look at what we're trying to make it look like. Whoops. We're trying to make it look like this guy right here. What is 1 over sine? Cosecant. And what is 1 over cosine? Secant. And then we've made it look like that side. Okay? So if you get stuck, writing things in terms of sines and cosines can really be helpful because they're the building blocks for all of the other identities. On this one, it works out pretty darn slick. Hopefully that's pretty easy to see. Any questions on that one? Okay, what's next? What other problems? 33 and 35? Okay. Okay, I'll grab 14, 33, and 35. You work on those. I'll get those copied to another page here. All right, ideas on number 14. Nathan, what's your idea?
Take the right side.
Take this side and put it in terms of sines and cosines? Okay. Is this side more complicated than this side over here? Okay. We can work on this side, but remember, we're better at putting things together, taking two terms and putting them into one, than we are doing it the other way around. Not that that's the wrong thing to do. Okay. It might be in this case. So if you want to do this right here, what are you going to do on this one? Put it in terms of what? Put it in terms of sines and cosines? Okay. So this would be, what is secant squared? So that's going to be, 1 over cosine squared beta over sine beta over cosine beta. Okay, and then what? Okay, so we're going to flip this one over, so that's going to be cosine beta. Quiet down, please. Okay, sine beta. Then we're going to cancel one of these, right? So what's that going to give us? Times sine beta. Okay, and then any idea where to go now? Okay, so this one we kind of barked up the wrong tree. It's not that we couldn't get there. It's just figuring out how to break this into two separate pieces is going to be kind of difficult. There are a couple things that we could do by working on this side. Let me show you what you could do on this side that might get us a little bit closer. Remember, if you have a trig function squared, it might be a Pythagorean identity. It's tangent squared plus 1 equals secant squared. So we could put tangent squared x plus 1 over tangent. And we could try that, and maybe that would get us closer. But I think generally it's a lot easier to take two terms and combine them to be one than it is to take one term and try and figure out how to break it apart. So let's take this and let's write this as 1 over sine beta cosine beta plus sine beta cosine beta. Right? That's just using a quotient identity. What can I do with this one right here? It's a number divided by a fraction. Do we ever divide by a fraction? Times by the reciprocal. So this is going to be cosine beta over sine beta plus sine beta cosine beta. Right? Any ideas here? Get a common denominator. So let's get a common denominator. This needs a sine beta. That needs a cosine beta. So this is going to give us, this is going to be a sine beta, cosine beta. And on the top is going to be a cosine squared beta plus sine squared beta. And what is cosine squared beta plus sine squared beta? What is this? Whoops, that should be a beta. What's sine squared beta plus cosine squared beta? Isn't that? It's a 1, right? So this is 1 over sine beta cosine beta. Now, at least we have one single term. I need a secant squared here. Is there an identity that has a secant squared and a 1 in it? It's the one we just had on the board. Tangent squared x plus 1 equals secant squared x, right? So if I were to move this to the other side, that would give me 1 equals secant squared x minus tangent squared x. Everybody okay with that? So that numerator can be a secant squared x minus a tangent squared x over sine, whoops, that should be beta, and cosine beta. Let's see. I have one single term. I want to make it look like this right there. I've got a secant. Got a secant squared. Any ideas? Does anybody figured this one out doing it a different way? Okay. What'd you do? Right here? Okay, so is this going to take us a while to get there? Yeah. Is there a shorter way to do this? Okay, does this mean we did anything wrong? No, it just means we barked up the wrong tree a couple times. Okay? Now, that can be frustrating, but it's not the end of the world. Again, these take some practice to do. So let's come back here. And if it's taking us that long to figure it out, let's come back here and say, well, wait a minute. What if instead of writing in terms of sines and cosines, because that's a good general idea, but it doesn't always work. What if we came back here and we said, look, like Jordan said, and Hope, did you do the same thing? Did you get a common denominator? Okay. The denominator right here is a 1, so I need another tangent. So I need a tangent beta here, and I need to multiply by another tangent beta there. That gives us 1 plus tangent squared beta on the top, and it gives us a tangent beta on the bottom. Wait a minute. In one single step, I've got a tangent beta on the bottom, which is what I want, and I've got 1 plus tangent squared beta on the top, which is Secant squared beta. Okay, now those other methods that we went through, tried working on this side, got to a complicated spot, tried writing in terms of sines and cosines, got to a complicated spot, just got a common denominator, and we're done in 2 steps. Okay? Are you going to see the exact best way to do it every single time? Nope. Nope. Okay, so it's a lot of practice in seeing what to do. What could have made this easier to see? Like Nathan wanted to work on this side, I wanted to change it into sines and cosines. What clues could we get from this side that might have helped us know this is probably the best way to do it? We've got to combine them, and we've got to have a denominator of tangent. If this already has a denominator of tangent, all we need is a common denominator of tangent, and we'll at least have the bottom right. That would be a good hint. Okay? All right. Any questions? Okay, let's take a quick look at 33 and 35, and then we'll probably be done. Okay. Peyton, what identities do we have to use on this one right here? Peyton, what identities do we have to use on this one right here? It wasn't, or it was?
It was.
It was. Okay, so what identity do you need to use first?
I did it on the right side.
You did this side right here? Okay. How come you chose that side?
It just looked easier.
Looked easier. Okay. What identities eventually we're going to have to use if this side is in terms of theta and this side is in terms of negative theta? Even and odd identities. So at some point at least we're going to have to change this to cosine of theta, right? Because cosine is even, it doesn't matter whether you plug in the negative of the angle or the positive of the angle, you're going to get the same answer, odd, even identities. And what about sine? Is sine odd or even? It's odd. Okay, so this is going to be 1 minus sine of theta. Okay? Yep. Okay. There are 2 separate terms here. This would be one where maybe it would be a good idea to work on both sides, at least to get an idea of what happens. That's one single step changing the format there. Let's take this one, and you'll notice we've got 2 separate terms, and I've got 1 term over here. That means I'm going to need to put them together. That means I'm going to need to get a common denominator. But these aren't even written with denominators yet. So what should I do with each one of these? Write them as 1 over cosine theta, sine over cosine. Isn't that right? Get a common denominator. What am I going to need here? I'm going to need a sine on this one and a sine on this one. Whoops. Oh, these already are a common denominator. Yeah. So this is going to be 1 plus sine of theta over cosine of theta. Now, looks pretty darn close. It's just upside down, right? And we're wrong sign here. We did one kind of like this the other day. Does anybody know what we do with this in order to make it look like this side over here? What's that? The conjugate. Very good. So we're going to multiply by 1 minus sine squared, or 1 minus sine theta, 1 minus sine theta. That's going to give us 1 minus sine squared theta, because remember, those are a difference of squares. And then over here I have cosine. Now, resist the temptation to distribute through there, because that's just going to make it worse. What's the numerator? Okay, that's a Pythagorean identity, so this is going to be cosine squared theta over cosine theta, 1 minus sine theta. I've got 2 of them on the top and 1 of them on the bottom. I can cancel this one with that one. And then I've got, come down here a little bit, cosine theta, 1 minus sine theta. There we go. Okay? That's a tough one. If you did get to here and needed to put the negative in there, you'd slide that in there using an odd even identity. And you'd have to recognize that if I write cosine theta, that's exactly the same as writing cosine of negative theta. Okay, that's a tough one. Let's take a quick look at number 35. I haven't done all these, but I think this one is probably the hardest
Yeah, I
one.
skipped this one.
This one's probably the hardest one. Okay? Okay, take a look at the hints that we've got here as to what we might want to do. Notice that both sides have how many terms? One.
What?
They're both a single fraction. There's a fraction over here and there's a fraction over here. Now, if they're both one single fraction, I realize this side has more stuff with it, but this side over here is tangents of x and y. It's probably going to be easier for us to take tangents and turn them into sines and cosines than it is to take sines and cosines and turn them into tangents. So on this one, I'm not saying this is the best way to do this one, but I think it might be. Let's write everything over here in terms of sines and cosines. So I'm going to write sine of x over cosine of x. Pay careful attention to the angle that we're plugging into this. It's y on this one. So this is going to be sine of y over cosine of y. And then in the denominator, you're going to have 1 minus, and let's see what we've got here. This is sine x, cosine x times sine y, cosine y. Now, that looks worse for the time being, but at least we have all sines and cosines. I've got sine of x, cosine of x, sine of y, cosine of y. Those are going to show up over here. What's the name for this expression right here? Complex fraction. How do we normally simplify a complex fraction? Yeah, we multiply by the reciprocal, but you've got to have a single fraction on the top and a single fraction on the bottom in order to do that. Okay? That's the most basic technique for solving a complex fraction or simplifying a complex fraction. Single fraction on the top, so we're going to want to combine these. Single fraction on the bottom, so we're going to want to combine those. So let's take a look here. I'm going to change colors here. What does this one need? It needs a cosine of y. So I'm going to write a cosine of y here and a cosine of y here. Multiply the top and bottom by cosine y. What does this one need? It needs a cosine of x. So I'm going to multiply the top and bottom by the cosine of x. So that's going to give me, let's see, the common denominator is cosine x, cosine y, and then I've got sine x, cosine y, plus, that is a plus, and then I'm going to write the cosine first, so that x is first and the y's are the second, and then sine. Okay, take a look at this and take a look at this. Is there any part of that that looks good? The numerator does. It's exactly what we need. Okay, so that's kind of good. Let's take a look down here now. If I'm going to combine the two of these together, this really is a single fraction. What denominator do I need here? I need a cosine of x and a cosine of y, and if I multiply the bottom by cosine of x and cosine of y, I need to do the same thing on the top. So here's the common denominator on the bottom. Common denominator on the bottom is cosine x, cosine y, and then I've got cosine x, cosine y, minus sine x, sine y. Quotient identities here. Common denominator from here to here, and then you should be able to finish that off. Okay? Well, let's talk about what you do. Whoops. what do you do with this right here? Take this bottom fraction, that is one single fraction. It is a gigantic single fraction. Take this one, flip it over and multiply. What's going to cancel? The denominator here with the numerator over here. So the cosine x, cosine y is going to go away. And what's going to be left on the top? This. And what's going to be left on the bottom? This. And doesn't that work out to be this side over here? It does. Okay? Yeah.
What I did was I factored out cosine of x times cosine of y of the numerator and denominator.
So you factored what out?
Cosine of x times cosine of y.
Oh, and then divided out? Excellent. Okay. Most people would struggle with that, I think. Okay. So here's what Jordan did, and we're done if you want to wrap up at this point. What he did is he factored out a cosine of x, cosine of y out of the numerator and out of the denominator. So what's left here is a 1, and what's left here is if you divide by cosine x and cosine y, you get minus tangent x, tangent y. Okay? Excellent. Good way to do that one. Okay? Lots of different approaches.
Are you going to give us a question like that on the test?
Not quite this difficult. Okay? Just didn't want to do it. Well, you're going to have to do the ones on the quiz tomorrow. No, they'll be pretty reasonable tomorrow. Okay? But some of them may be a little challenging, so make sure